Factoring special products. In this video, we'll look at two special products. One is called a perfect square trinomial, and the other one is called the difference of perfect squares. Let's start by reviewing what it means to square a binomial. So if I asked you to square x plus 6, that would mean multiply it by itself. We could use FOIL or double distributive or box, and we would get a trinomial, x squared plus 12x plus 36. Turns out this trinomial is called a perfect square trinomial because it's the result of having squared a binomial. So anytime we end up with a trinomial that is the result of having squared a binomial, we're calling it a perfect square trinomial. Now let's look at the structure of this type of trinomial. The first term will always be a perfect square. The last term will be a perfect square. The middle term will be twice the product of the square root of the first and the last terms. So let's look at that a little bit more closely. In this example, the square root of the first term is x. The square root of the last term, the square root of 36, is 6. If you multiply those two together, you get 6x. If you double it, you get 12x. Therefore, this particular trinomial fits the structure of a perfect square trinomial. And remember, it is the result of having squared a binomial. Therefore, it factors into x plus 6 quantity squared, where x is the square root of the first term in the trinomial, and 6 is the square root of the third term in the trinomial. And I have a plus in between the two terms because the trinomial had all plus signs. Right, so now let's decide if any given trinomial can be classified as a perfect square trinomial. The first term is a perfect square. Yes, x squared is the result of x times x. 9 is a perfect square because it can be written as 3 times 3. The middle term, 6x, let's check that it's twice the product of the square root of the first and the last terms. Okay, the square root of the first term is x, square root of the last term is 3. Multiply them together, you get 3x. Double that, you get 6x. Yes, the middle term is twice the product, therefore this is a perfect square trinomial. Because of that, it can be factored into some binomial squared. It can be factored into x plus 3 quantity squared. So when we find a perfect square trinomial, it can be factored very easily. Here's another example. To determine if this is a perfect square trinomial, I do notice that there is a GCF of 4 which can be factored out. And this is helpful because 4 is a perfect square. So if the remaining trinomial is a perfect square trinomial, then the original one as well. So let's check each criteria. The first term, 9x squared. Yes, that's a perfect square. The last term, 4. That is a perfect square. Now I'm going to take the square root of the first term, that's 3x. The square root of the last term, that's 2. 3x times 2 is 6x, doubled is 12x. In this case, the middle term is twice the product of the square root of the first and the last term. So this is a perfect square trinomial. It can be factored into 4 times the binomial 3x minus 2 quantity squared. Don't forget to bring the 4 into your factored expression. Now let's go on to another type of special product called the difference of two perfect squares. X squared minus 4 classifies as the difference of two perfect squares because the first term and the second term are both perfect squares, and there is a subtraction sign between them. And so whenever you have an expression like that, it factors very nicely into the square root of the first term minus the square root of the second term times square root of first term plus square root of second term. And you can have your plus and your minus in either order. Right, so let's consider, is d to the 10th a perfect square? Well, although 10 is not a perfect square, d to the 10th is, because it can be written as d to the 5th times itself. Turns out a variable raised to any even exponent is always considered to be a perfect square. So keep that in mind as we factor these examples. 4x squared minus 25, both terms are perfect squares. There's a minus sign separating them, so this factors nicely into 2x minus 5 times 2x plus 5. Here's another example. 9m squared minus 16t squared. Can I use the difference of perfect squares to factor this? Well, both terms are perfect squares and there is a subtraction sign between them, so indeed this can be factored 3m minus 4t times 3m plus 4t. Two more examples to go. 36x squared minus 12x plus 1. Well, that's a trinomial, so I'm not going to use the difference of perfect squares, although I do see a perfect square in the first term. And I also see a perfect square as the last term. This might be a perfect square trinomial. I'm going to take the square root of the first term times the square root of the last term. That's 6x times 1, that's 6x. And I'm going to double it, that's 12x. Yes, this is a perfect square trinomial. It can be factored into 6x minus 1 quantity squared. Now this last example, while both terms are perfect squares, and I could certainly factor using the difference of perfect squares, I'm also noticing that there's a common factor of 9 which can be factored out. That's going to be helpful because 9 is a perfect square. Now the remaining binomial, both terms are perfect squares and there's a subtraction sign between them. So it's 2x minus 3y to the 5th times 2x plus 3y to the 5th. And don't forget that factor of 9 that you had taken out.